All right, so we're going to be working on chapter 4, lesson 6, and we're going to be talking about functions. So, the learning objectives for today are to determine whether a relation is a function and find the values of functions. Some of the vocabulary to keep in mind are what is a function, the vertical line test, and function notation. So, how are functions used in meteorology? So the table shows barometric pressures and temperatures recorded by a national climatic data center over a 3-day period. So here is the pressure outside, and here is the temperature outside. And so notice that when the temperature, I'm sorry, notice when the pressure is 995 and 1006, right? There's more than one value for the temperature. So here you can see um, that here the temperature is 4 degrees Celsius, but it's got a pressure of 1,000. And here it has a um, uh, barometric pressure of 1,006. And you have 4 degrees Celsius. And here, same thing. You have the same pressure outside, but two different temperatures. And so noticing that if you have the same pressure, you can have two different temperatures, or if you have two different temperatures, you can have two different pressures. And so that's some of the stuff that we're going to be looking at as far as functions. Is if you have the same pressure outside, should you not have the same temperature, and vice versa. So how do you identify a function? So recall that relations, right, those set of ordered pairs that we talked about in previous lessons, in which an element of the domain is paired exactly with one element of the range is called a function. So basically, remember your domain are your x values and your range is your y values. So basically, as long as one x value is only paired with one y value, then that's what's known as a function. So here's the key concept. A function is a relation in which each element of the domain is paired with exactly one element of the range. Again, just solidifying that for each x value, you can only have one y value. Okay, so if your x value is 4, whatever your y value is paired to, right, that ordered pair, if you ever see that x value again, it should have that same number. It should not have the same x value with two different y values. So here's a study tip. In a function, knowing the value of x tells you the value of y, right? So for every single x, there is a specific y value that is paired to it. All right, so let's identify functions. So we're going to determine whether each relation that is shown is a function, and we're going to explain why. So let's look at these three relations, right? Here's a mapping that we've talked about before. Here's our domain, our x values, and it's paired with the range, the y values. So I have -4, 9, -1, -6, +1, -6, and 3, 11. So here you would say, oh, look, -1 and +1 are both paired with -6, which is actually okay because each x value has its own specific y value that it is paired to. Okay, so this is what is known as a function. This is okay. It's okay if you have two different x values with the same y value. What wouldn't be okay is if you had the same x value with two different y values. So it's okay if we repeat y values, but we should not repeat x values. So let's look at this one. This table represents something that is not a function, just like what I talked about before. If -3 is paired with 6, 2 is paired with 5, 3 is paired with 1, then 2 should again be paired with 5. It cannot be paired with a different number, 4. So notice how we have repeating x values with different y values. This is not okay. This is not a function. So it's okay if different x values have the same y value, but is not okay if the same x value has different y values. Okay, so this instance where these guys share the same y value is okay, but the same x value should not have different y values. So this is a function. This is not a function. Now let's look at this final one. We have negative 2, 4, 1, 5, 3, 6, 5, 8, 7, 10. This would be an example of a function because if you notice, each x value is different and it has its own y value. So this would be known as a function. Okay. The other way we can look at functions is if we're looking at a graph. And when we're looking at graphs, it's really easy to tell if something is a function if it has repeating x values, and that's by using the vertical line test. If no vertical line can be drawn so that it intersects the graph more than once, then the graph is a function. If a vertical line can be drawn so that it does intersect the graph at two or more points, the relation is not a function. So what do all those words mean? Well, let's look at these three graphs right here and see if they're functions by using the vertical line test. And basically, if I have a vertical line that I can drag across, and if it ever touches it more than one time, if it touches it two or more times, then it would fail as a function, right? So let's try that. So, and this is what's known as the vertical line test. So I'm going to drag a red line across here. And when I did that, notice how the vertical line never touched the graph more than once. It only ever ran across it and touched at one spot at any given moment. Let's look at that again. Let's look at this vertical line running across. It only ever touches it at one spot at any time. Okay, so this would be considered a function because if I ever touched it in two spots at the same time, that means that you would have the same x value for two different y values, which is not okay in a function. Let's look at this graph here. So again, I'm going to use my vertical line test. And if I use my vertical line test, I'm going to drag it across and what do you notice? It touches it in two spots at any given moment here, right? If I were to take this vertical line and move it side to side, it would touch it in two spots. Now this would tell me that I have a point with the same x value, but two different y values. So this would fail the vertical line test and would be known as not a function. Let's look at this guy here. Again, we're going to do the vertical line test. We're going to drag this vertical line across the graph and it actually passes. Some of you might say like, oh, well, what about here? I have a point here and a point here. Well, that's not true. Notice how this point is solid and filled in. There does exist a point there. Over here, I have an open empty circle, which means there is no point there. So on this vertical line right here, I only have a point here and not here. And then once I get past it, I only have points up here. Once I get to the left of it, I only have points here. So this would pass the vertical line test because the only possible place where it could hit it twice is here. But again, a point exists here, but not here. So this would be considered a function. So a vertical line test is an easy way if you're looking at a graph to tell if it's a function or not. So let's look at some examples. So here it says equations as functions. Determine whether 2x minus y equals 6 is a function. So if you only give you the function or the equation of the function, guess what? You have to graph it. So let's go ahead and graph this. I'm going to use the x and y intercepts to graph this. And if you remember, the easiest way to do it is you can find the x-intercept by letting y be 0 because that's where x-intercepts occur. And you can find the y-intercept by letting x be 0 because again, that's where y-intercepts occur. So I'm going to take my original equation and I'm going to substitute 0 in for y. When I do that, 2x minus 0 is 2x. So 2x equals 6. Again, use your equation solving, divide both sides by 2. And then that gives me x equals 3. So now I know that my x-intercept occurs at positive 3. Let's go over here and let's do the y-intercept. Again, I'm going to take my original equation. I'm going to substitute 0 in for x now to find the y-intercept. So 2 times 0 is 0, which leaves me with 0 minus y, which is negative y. And so I have negative y equals 6. Again, I don't want to know what negative y is. I want to know what positive y is. So an easy way to do it is either multiply or divide both sides by negative 1. I'm going to divide both sides by negative 1. When I do that, a negative divided negative is a positive, and a positive divided by negative is a negative. So I get y equals negative 6. So now I know my y-intercept occurs at negative 6. My x-intercept occurs at positive 3. That would allow me to make my graph. Again, I could put a point for my x-intercept at positive 3, put a point at my y-intercept of -6, and then just draw my line between those 2 points to make my line. So this is the graph for this equation. Now, I'm going to go ahead and examine this graph. Is it a function? Well, since it's a linear equation, right? I can see it right here. I'm going to go ahead and do my vertical line test. And again, it's also known as the pencil test because you can take your pencil. There we go. You can take your pencil and just run it across the graph with your pencil and test it yourself. Okay, that's what I usually do is I just look at a graph and take my pencil and just kind of run it side to side on the graph. And if the pencil ever touches it more than one time, if it touches it 2 or more times, then I know it has failed the vertical line test and it's not a function. But if I can run my pencil across it and it only touches it no time or one time, that's okay, then it is a function. Okay, so let's go ahead and let's do this. So there's our vertical line test, sweep it across. It never touches it more than one time. So therefore it is a function. So for each value of x, I know there's, because of the vertical line passes through no more than one point of the graph, the line represents a function. So let's look at this now. So we have function values. So equations that are functions can be written in a form called function notation. So this is one of our vocabulary words. Function notation is really similar to what we've kind of dealt with before. It's just a different way of writing it. And so a normal equation that we would see is like y equals 3x minus 8. Okay. Function notation, if I were to write the same equation in function notation, this is really standard notation. Function notation replaces y with f of x. Okay. And that's how I would pronounce this. And here's the study tip right here. This symbol right here is read as f of x. F being the name of the function and x being the input. So basically this is my equation where I input x. Okay. So it says in a function, x represents the elements of the domain and f of x represents the elements of the range. So basically your x's are still x and your f of x is your y value. And so it says, suppose you want to find the value in the range that corresponds to the element 5 in the domain. Basically, what does that mean? It means that you are putting x in for, or 5 in for x. So this is written as f of 5. So instead of putting in an x, we're going to put a 5. So f of 5. So the value f of 5 is found by substituting 5 for x in the equation. Now, I know that's a lot of words, so let's look at what this, how this plays out in action. So we're going to find function values here. So here, again, we're going to read it correctly. If f of x equals 2x plus 5, find each value. So here they give me 3 examples. So here I'm finding f of -2. So what does that mean? Instead of having an x, what am I going to put in its place? I'm going to put -2. So everywhere there was an x, I'm putting -2 in, right? So instead of 2 times x plus 5, it's 2 times -2 plus 5. And then I just have to calculate this side. I don't have to do anything to the left side. I am only calculating the right side here. So 2 times -2, right, is -4. -4 plus 5 is 1. So now I know f of -2 is equal to 1, right? So this would be the same thing if it said y equals 2x plus 5 and I plugged in -2, it would say y equals 1. But instead of using standard notation, we're using function notation. And this is really important because this tells us what we input into the equation and what our output is. What is our equation equal to when we input -2? All right, let's go ahead and look at B now. So here, this one, they added a little bit of complexity. We're finding f of 1 plus 4. So we're going to take our f function, our equation, and we're going to plug 1 in for x, and we're going to do that, and then we're going to add 4 to it. That's all that means. So let's look at it. So I have f of 1 plus 4. So I'm going to take my f of 1, right? So this equation. So 2 times 1 plus 5, right? I'm going to do all that first, and then after I'm done doing that, I'm going to add 4. And that's what these brackets are. Basically, it's like a grouping symbol, like a parentheses. I'm going to do everything inside of here first, and then I'm going to add the 4. So let's go ahead and do this. 2 times 1 is 2, and then 2 plus 5 is 7. So I did everything inside now. And then I'm going to do 7 plus 4, which is 11. So now I know that f of 1 plus 4 is equal to 11. Again, notice I didn't do anything to the left-hand side. All I did was input my value and calculate the right side. Now we're going to do the same thing with C. Now this one looks a little bit weirder because look, we have a variable inside. We're inputting x plus 3, but we're going to do it the exact same way. The only difference is our answer will not end up as a number, okay? So here I have f of x plus 3 equals, again, our equation is 2 times x plus 5. So we're going to do 2 times x plus 3 because that's where we're putting in. So instead of x, we have x plus 3 plus 5. Okay? So again, we just took this regular equation, we replaced x with x plus 3. So now that we've done that, now we can calculate it out. We'll use the distributive property, right? 2 times x is 2x. 2 times 3 is 6. Now that we've done everything inside of the parentheses there, now we can simplify. And I know I can do 6 plus 5. 6 plus 5 is 11. 2x plus 11 cannot be added together because they're not like terms. They both don't have x's. So that is as simple as I can make it. That's now simplified. So my answer to what is f of x plus 3, that is 2x plus 11. And that is my final answer there. So again, our main idea for finding function values is just inputting what it tells you to input into your equation. We're just substituting, we're replacing and simplifying. So obviously, if we're just inputting a number, we're going to get out a number. If we're inputting a variable, we're going to get out something with a variable. Let's look at another one. Functions that we've studied so far have all been linear functions. However, many functions are not linear. You can find the value of these functions in the exact same way, though. So we're going to take a look at a couple of these. So we're going to look at some nonlinear functions here. So here we're going to take a look at these three values here. So here it says if h of z, remember how you read it, h of z equals z squared plus 3z minus 4. So normally we're inputting x, right? Here they're asking us to input for z. And instead of the name of the function being f, here they name the function h. Again, it doesn't change anything. It's still done the exact same way, okay? So h of z equals z squared plus 3z minus 4. So here, same thing. I'm using this equation here, and instead of plugging in z, what am I replacing z with? I'm replacing it with negative 4. So let's go ahead and do that. Everywhere where there was a z, I put negative 4 in its place. Now here's really important. Make sure you follow your order of operations. I want to do the exponent first. So what is negative 4 squared? Some of you might tell me it's negative 16, which is not correct. Remember, what is negative 4 times negative 4? A negative times a negative is a positive. So negative 4 times negative 4 is positive 16. And then I would do this part. 3 times negative 4 is negative 12. So I'd have 16 minus 12, right? Because they became negative 12, minus 4. And so then you simplify that, and that would give you 0. 16 minus 12 is 4, and 4 minus 4 is 0. So now I know that h of negative 4 is equal to 0. When I input negative 4 into my equation, it equals 0. Let's go ahead and do the next one now. So now it says h of 5a. So again, in this equation, the h function, I'm going to be inputting 5a. So these z's that you see will now be replaced by 5a. So here we go. Everywhere there was a z, now there is a 5a. So now we're going to do it the same way. We're going to go ahead and simplify this. We're going to do the exponent first. So 5a squared means 5a times 5a. Well, I know 5 times 5 is 25, and a times a is a squared. And then I'm going to do 3 times 5a. 3 times 5a is 15a. Okay, so I have 25a squared plus 15a minus 4. So one thing that you'll notice is a squared and a are not like terms. In order for something to be a like term and be combined, they have to have the same variable, and those variables have to have the exact same exponents. So these three terms cannot be combined together, so that's as simplified as it gets. So h of 5a equals 25a squared plus 15a minus 4. That is the final answer for that one. Let's go ahead and look at C. So C looks a little funky. Here they're saying, hey, take the H equation and input G. Well, that seems easy enough. But after all of that, you're going to take the equation and multiply it by 2. So let's try that. So again, we're going to take the H equation. We substituted G in, and then we're going to multiply it all by 2. So this, again, seems a little bit hard, but it's not. Notice how the equation went from having Z's in it to now having G's in it. And now I just have to use the distributive property and multiply everything by 2, right? So 2 times G squared is 2G squared. 2 times 3G is 6G. And 2 times 4 is 8. So I have 2G squared plus 6G minus 8. So the 2 times H of G equals 2G squared plus 6G minus 8. And that's how you do it. So again, it might look a little bit complicated at first, but really you're just substituting values into the correct spot. Again, you can write these down, follow the same pattern. And again, if you guys have any questions, reach out to me. But that's how we work with functions. Thank you guys for watching, and I'll see you.